Hello explorers and welcome to another video. Today we are doing the Advent of Code puzzle. The Git repository is linked in the description below, and if you want to see all of my trials and tribulations, you can see the full recording as a member of this channel. Day 12, Hill Climbing Algorithm. You try contacting the elves using your handheld device, but the river you're following must be too low to get a decent signal. You ask the device for a height map of the surrounding area, your puzzle input. The height map shows the local area from above, broken into a grid. The elevation of each square of the grid is given by a single lowercase letter, where A is the lowest elevation, B is the next lowest, and so on up to the highest elevation, Z. Also included in the height map are marks for your current position, S, and the location you should get the best signal, E. Your current position, S, is the elevation A, and the location that should get the best signal, E, has the elevation Z. You like to reach E, but to save energy, you should do it in as few steps as possible. During each step, you can move exactly one square up, down, left, right. To avoid needing to get out your climbing gear, the elevation of the destination square can be at most one higher than the elevation of your current square. That is, if your current elevation is M, you could step to an elevation of N, but not an elevation of O. This means that the elevation of the destination square can be much lower than the elevation of your current square. For example, here it could be start left corner, your goal is near the middle. You could start by moving down or right, but eventually you will head towards E. At the bottom, from there you will spiral around to your goal. In this diagram above, the symbols indicate whether the path exists, each moving square to the location with the best signal, still E, and dot marks unvisited squares. This path reaches the goal in 31 steps, the fewest possible. What is the fewest steps required to move from the current position to the location that should get the best signal? Get your puzzle input. Yeah, let's do that. Day 12. So let's get into this. I want to look at the puzzle input. Jesus. That is a lot. So we have 41 and 180. Yeah, that's a lot. That's a lot. So let's start by fetching our start square here and put it into this little piece here. And I think I will do as I did in one of the earlier examples here, create a string list of just the inputs. So we know how many rows and how long the rows are. List, add line. Just do it like that. And then we will create a little bit of a grid. List size times list get 0 size of length. So that should be if line is blank and continue. So we don't take any blank lines. lists, each string of the list. So this is the elevation grid. And split it by anything. Then we will get all the letters. And for each letter, I just do it like that. Get bytes minus 65, for instance. Like that. We do minus 65. So let's see here what we get. We are still at day 11, of course. So do it like that. Debug. So this is 83, that's the first letter. And that's because it's an S. So if L equals S, and then else if E, else, we do it like that. So do something different for S and E. So now we have 32. Yeah, so they start at 97. So let's remove 97 then. So we will get 0 there. And if it's an S, we will start that at 0 as well. And E will be 25, right? Or is it 26 letters in the English alphabet? So like that. So now we have all of those. I think we still need X and Y as well to figure out what position it is. We could have a byte grid as well. let's stick to an int grid. I don't think it will be that large. So we need to know where it starts. We need to know where it ends, and we need to figure out y plus plus x plus plus. Start x, start y, end x, end y, start x, start y, end x, end y. Like that. So now we should have a bunch of values here. So let's create a path. So we have a new class here called a path. And a path has a new path. And a path has a starting position. And you also have a size. So we have the list gets 0 length and the list size. So now we have a path here with a constructor that is start x, max x, max y. And this path should have a private Boolean visited. We should have a private final int start x. We should have a bunch of those. Y max max. Y max max. There we are. And this visited should be equal to new Boolean with the max x times max y. So now we have the visited. Have a current x. I don't think that we actually need the starting position, right? And we can also do this visited max x times start y plus start x. True. And here we should also do an arrays fill visited with false. So we know that all the visited squares are false. So there we go. Then we can have a function here, public list of path, get new paths. Current x minus 1. Max x times current y plus that. So if that is false, then we can pick up a path from there. So we should have a bunch of these. List of path, new paths. And then we will return new paths. So that's what we want to do. We should have one plus here. Then we should have one minus 1 here. And then plus 1 here. So one path could create 4 new paths. But the case could also be that current x must be larger than 1, or else that would not be allowed. And here, current x must be lower than max x minus 1, or else we can do that. And the same goes for these. Current y must be larger than 1, and current y must be smaller than max y minus 1. So that's just so we don't get out of bounds. And if this is true, we will create we can have the same function here again. The only difference is that we will add a visited thingy, so we can have that as well. This start x, start y, max x, max y, visited equals visited. Like that. So here we can take new paths, add a new path, new path, where current x minus 1, current y, max x, max y, and then arrays, copy of visited. So the size of visited, so we copy the full one. And then we do the same for the other ones here. Plus 1. Make it a little bit more readable. We can use multi-line. And we can also remove all of these extra bits here, so we have a little bit more viewing area. Sorry for that. Plus 1. Minus 1. And last but not least, plus 1. So now we have a bunch of new paths here. So that is our path function. And then we will have a new function here, public boolean at found end. And then we will have end x and y. Return if end x is equal to current x and end y is equal to current y. So now we have a way of finding the last path. So here we'll have a list of path, which is current paths. New list. No. Array list. We also need to have a length, right? Private int length. Even have a final length. So this will just have length of 0. And down here, no, I can't have that. Yeah, let's remove final. This length is equal to length. length value there as well. And at the beginning it starts at 0. So here we just do length plus 1. So there we go. So now we can find a bunch of different paths. We also need to keep track of the elevation, right? So private int elevation, current elevation equal to 0. Current elevation. Yeah. So here we will have the grid of elevation grid. So this will be elevation grid and current x times max current y times max x plus. So it's similar to what we did above when we checked the visible map, but for our elevation grid. So plus there. That. I need, of course, to add it here as well, so we are sure that we do the plus and minus before we actually do the times. So now we have the elevation grid for that specific position. And we also need to here have an extra condition if this is smaller than current elevation plus 1, smaller or equal to. So that is a requirement as well for the new path, right? So smaller or equal to current elevation plus 1. Yeah. Let's continue to write it like that, or else it will be very confusing. Smaller or equal to current elevation plus 1. And last but not least, we write a lot of code before we actually got to test this out, so this is going to be interesting. Current elevation plus 1. And there we go. What is wrong here? Visited. There we go. Yeah. So now we have current paths. We add that first path to the current paths. We could have yeah. So we will do a for loop of path, p of current paths. And if p found the end, and we can have final paths here. If this is true, then final paths will have p like that. Else we will take we will have another list here with paths, that is new paths. Else we will take these new paths and add all the paths that we get from p get paths of the elevation grid. And down here we take current paths is equal to new paths. And we will do this while current paths is not empty. So at some point we will not get any new paths because we can't create any. So let's see if this just locks up or if we actually get here at some point. And now I think we need to do actual pruning and early pruning. So I think that we actually can think about the problem a little bit differently. When we take a step, we take all the steps available for that iteration. So we create all paths from step 1, step 2, and so on. So that will always be the shortest path that we have taken to that spot at the moment. So we could actually create a visited map that is not a part of this function at all. So we don't need to have this in this class. And I also created this visited map that is sorted and so on. But I don't think that we need that either. We just need to have a bunch of we just need a set of visited paths. Here we can have a set of integer visited. So we go back to that part again. And then this visited does not contain this point here. like that. Remove visited there. Continue here. So I will fix this up. And the last part here. Like that. And I had a function for checking if something contains in an array. So get new paths visited. So here we have this, and we need to add visited. So what we want to do here is to have a set of integers, visited, new hash set. So there we go. And then here we will take for all the new paths. We will go through those, and we can actually add it here. So visited, add p get ID. And what is ID then? ID is return current y times max x plus current x. So then we will have a way of visiting that path, and it will be the shortest path to that visit. So if we run that, we hopefully will not run out of memory, at least, and we might get a somewhat good result. I think if we have one final path, that will be the shortest as well. So we can actually do a break here. And we are back, and after 19 minutes, we ran out of space again. So I think that we need to create some kind of hash set, map integer path, current new paths, and then new hash map, so that we don't create a bunch of paths that we don't need. So get the values here, new array list of those values, like that. We could also say that we want to have collection of paths here. That's actually valid. So then we don't need to create a new array list, because we actually just want the collection that we can go through here. So we create a new hash map every time, and then we will put the ID of each of these. So we need to actually loop over them. For P1 of those, put them in here. Then we don't get multiples of them for each run. It will take a bit more time, or don't. It might also go very fast. That is also an option. So that was a good choice. I wonder if we get the same result if we run the old version here. Yeah, we got 31. So 517 might be the right answer then. Let's see. Put it in here. Yes, you get a gold star. I get a gold star. Everybody gets a gold star. So let's continue with part 2. As you walk uphill, you suspect that the elves will want to turn this into a hiking trail. The beginning isn't very scenic, although perhaps you can find a better starting point. To maximize exercise while hiking, the trail should start as low as possible, elevation A, and the goal is still the square marked E. However, the trail should still be direct, taking the fewest step to reach its goal, so you need to find the shortest part from any square at elevation A to the square E. Again, consider this example above. Now there are 6 choices for starting position. 5 marked A plus the square S. That counts as being at elevation A. If you start at the bottom left square, you can reach the goal most quickly. This path reaches the goals in 29 steps, the fewest possible. What is the fewest possible steps required to move from starting from any square with the elevation A to the location that should get the best signal? Okay. So we pretty much need to do as we did, but just add all the A's in the list. That might be the solution, but we still might run out of memory again. So let's try it. So we have a start X and start Y here, but we actually want to go through the elevation list and add all of them. So we can do an int y less than the list size y++, like that. Let's do y1 and x1. And then we will add paths here with x1, y1 if the elevation grid at y1 times max, max is this one, plus x1 is equal to 0, then we will add it. So if we run that, we get 29, which is the right solution there. So let's run out of memory then. See if we can do this or if we can't. 512. Could that be the right solution? Yes, you get a gold star, I get a gold star, everybody gets a gold star. So that was the correct solution for part B of this challenge. Much easier than part A because we ran out of memory a lot. But what we actually did in the end was that we created a bunch of easier ways to keep track on both what we have visited, because we always move further and further away from where we are, so we could have one visited map. We had luck with the second, I guess, the second approach. And then we could go through all these paths and find the shortest part here. And we go through them and we actually find what is the next shortest path from where we are at the moment. And we also only want to keep the ones that are unique paths. So if we have visited this one before, it's the shortest one. We don't have a shorter one to this specific point, so we don't need to keep that. So for every iteration, we move one step, and that is one step. So that's the shortest one to that point. We will add that to our visited map because we can't go shorter to that specific point at the moment. And we also remove any extras here, so we don't have any duplicates. We fetch those values. And the last part we do here is break when we get one final path, because that is the shortest one. So this final sort here is probably just not important. And then we type out the length of the shortest path. So this is today's advent of code. I hope that you found this interesting. I hope that you learned something. If you like this video, give it a like, share it with your friends and colleagues. If you haven't subscribed yet, please do that. If you have any comments or suggestions or some code for this specific day that you want to share with me, then please do that in the comment section down below. And I really hope to see you in the next video.